Hello everybody. Here in this video I'm going to teach you how to model a DC motor in static space, and then how to place its slow poles into a faster, better positions, and then we will have some observer for that model. And also we will see how we can model this in Simulink, MATLAB, and see the results. Let's start then. In this approach we will have three main steps. At first we will model a DC motor in static space. Second, we will design a gain matrix feedback for that model, and at third step we will design a full order state observer, and then we will see the simulation results together. Here are mechanical and electromagnetic equations for a DC motor, which is well known during 1980s. Here we will have two parameters, which the first one is angular speed and it is output, and next we will have an input, which is voltage of the armature. Here is the mechanical equations for the DC motor, and shaft speed will be our output. Using these equations we can extract our static space model. For that we will suppose two states for our model: x1 as shaft speed and x2 as armature current. Then we can rewrite our equations in a form that you can see here, and our output will be omega, which is shaft speed. Using matrix form we can see how our static space model can be obtained, and A, B, C matrices can be written as seen in this slide. Using parameters for unknown motor variables, we can have such a full static space model for the DC motor, and we will analyze this motor under an initial condition of 10 RPM for the speed and 0.1 amperes for current. Here you can see how we can model this static space model for DC motor in MATLAB Simulink. We can use either of these two models. One is MATLAB's own static space model, and the second one is designed using blocks. I normally prefer the second one because I can see the states much better than the higher one. Here in this model we can set the input voltage as a 12 volts and see how the speed of the motor changed over time. Using a 12 volts input, you can see that the speed goes up to 50 RPMs, and using the same input for current for the input, we can see the current decreases from something near 2.4 to 0.4. Applying a 50 volt pulse signal into the voltage input of our model, we can see the speed and the current of the motor changed as seen on the screen. Now it's time to design a feedback for this model so that we can place the poles on our desired positions. But for this, first we need to calculate rank of a matrix called MC, which is controllability matrix. We can see that the rank for this matrix is 2, which is equal to the size of our A matrix, and it means that our system is controllable. So we can calculate our feedback matrix. For this, we can write a determinant of S multiplied by I minus A plus BK, and calculating this determinant, we can see that we will have a second order equations as the equation you see on the screen. This will be used to place our poles. System's poles in original form are on -3 and -397, which means that system is too slow. We want to replace these poles both into -10, so we need to rewrite our desired equation and use to make it equal to our controlled equation. And solving this, you can see that we get two parameters for gain matrix, K1 and K2. Using MATLAB commands, you can see that Aker method produces the same results as we did on the screen. To use these parameters, these two gains on our system, you can see that we added two feedback gains in red on the screen to our Simulink model. So we multiply x1, which is speed, to K1, and multiply current to K2, and sum it with the input signal. Using this feedback, we can place our poles into -10. To do the same with the state space model of the MATLAB, you can write the A matrix as A minus BK. This will produce the same result for you. The main problem until here is that we placed our poles to a new position, but it doesn't, and it is normally called as a controller, but it doesn't track our inputs. What can we do to guarantee tracking our input by our output? The solution is state feedback integral control. To use that, we will augment a new variable called error. Of course, it is the difference of input and output, and we will augment it as our new variable into the model. Using this, the new state space model for our DC motor will be the way seen on the screen. And to see if this new model is controllable, we need to calculate the rank of a new matrix including B, A, 0 and A minus C, which if its rank is full, then the new system with new parameter will be controllable. And the gain matrix, gain method to control the system at the same time with the tracking inputs will be such as seen on the screen, which the first part is our normal state space feedback control method, and the second K2 is our new tracking control. To do this, we will use the same model in our previous section. We will add a new feedback from the output to the input, and we will add an integrator and also a gain parameter which is inside the rectangle here. Determining the gain used here is an easy method. You can use trial and error, or if you want to find the parameter optimally, you can use one of the evolutionary methods like genetic algorithm, PSO, or any other methods. Using this, you can see that our input will be tracked by our output. Here, for example, we entered our 60 volts input to the motor, and we got a 60 RPM in our speed as our output, and it just takes 2 seconds to settle down. At the third and final step of this study, we will design a full order state observer for our DC motor. To do this, you know that our observer equation, full order state observer, of course, is the way you see on the screen. It needs matrices of A, C, and B from our original model, and there is an unknown parameter, an unknown matrix like L in the model. Here in this schematic, you can see how we can implement an observer to our DC motor with a pole placement controller. As you can see, we use A, B, and C matrices from our original model, and we added an L matrix in our feedback down there. Finding L has many different methods. One can use Ackermann method or a Sylvester method as implemented in MATLAB. Here in this study, we used Sylvester method, and it produced such good results for our simulation. To see how good the speed as the state is observed by this observer, we can see this simulation. The higher plot is our real speed as changed over time by an input signal of a pulse form in the input, and at the bottom you can see the observer states, which are estimation of the real speed. Here you can see that our observer works perfectly, and the difference between input and output, input and the real state, is such a little ignorable and neglectable value of 10 to the power of minus 12. So we designed and modeled a controller for our DC motor. We used pole placement. We designed a integral controller to track the input, and we also designed an observer for that model. Using the same methods, you can design and place poles of any other models you have in hand for your projects. And if you have any questions or any problem solving your in-hand project, please don't hesitate to contact me.